All right, kids. So we are on with heating curves. And what we did to start with that is you should have done this interactive that we had in class. And as you can see, there's three different substances here. There's these dusty things and the sort of gemstone looking thing, and then these metallic ball looking things. And if you choose one, what the program will do is heat it up. So this is a hot plate. It's just going to turn that hot plate on. You're going to see what happens. So if I turn the purple gemstone down, it'll come down here. And then they'll put a thermometer in there. And what you were supposed to recognize is when you heat something up, it gets hotter until the point where it starts melting. And when it's melting, there is no change in temperature. And then when it's all liquid, it then heats up again until it gets to a point where it's boiling. And then when it's boiling, there's also no change in temperature. So here, where you're trying to find the melting temperature, you're looking for the flat part here. I believe that was 47. Work. I don't know why that. And then up here, you can see the boiling point is where it is right now, 143. So hopefully, it's kind of cool. I get that little. Right. So that was what you were supposed to experience, and that's true with any substance. So if I go here to, I guess, the green ones, all right, they're solid, and there's a point where you're just heating up the solid, and now we're just heating up the solid, and then when it melts, the temperature doesn't change. It stays at 30, and then when it's all melted, it's heating up the liquid, and then there's a point where the liquid starts to boil, and then the temperature doesn't change again. So as you can see here, the melting temperature was 30, and the boiling temperature is where we are now, 121. And then actually, after when all this liquid would become a gas, then the gas can get heated, and we hopefully learn that with PV equals nRT. So let's go on to this. All right, so what we learned there is that for any substance, and we usually just use water, you have what we call a heating curve, and this is as you're heating it, the time of heating. You will increase the temperature if it's just a solid, and then it'll keep increasing to a point where it melts. And when it melts, there's going to be a flat point because there's no temperature rising and solids becoming liquid and something like that. So when something is a solid, liquid, or gas, and you're giving it more kinetic energy, the temperature can change. These other times when there's a phase change, then temperature is constant. And the reason temperature is constant, so we're talking about here and here, right? At 100 degrees for water, where it's boiling, and at 0 degrees for water, where it's melting, you are giving things greater freedom. So it's not so much a kinetic energy thing, but a freedom from each other thing. So you're breaking the bonds between the atoms or molecules and giving them more freedom so that a solid can become a liquid or a liquid can become a gas. And that's where all that energy is going. And as we've discussed before, there's energy needed to go in one direction and energy removed to go in the other way. So this is endothermic to go this way, and it's exothermic to go the other way. And okay, so to do that, you're going to use these formulas now. We're not going to use the heat is equal to the specific heat times the mass times the change in temperature, because there's no change in temperature. There's no change in temperature. So we can't use that equation we've been using. We've been using the equation about changing temperature with specific heat and mass. But if the temperature doesn't change, then you're not going to be able to do that. So now we're going to use one of these two equations, which is the mass times the delta H fusion, or the mass times the delta H vaporization. Luckily, modern culture has told us what vaporization is. Fusion has to do with a solid turning into a liquid or a liquid turning into solid. I have to give you this number, but look at the units. The units are joules per gram. And because of that, if you're looking for heat, which is joules, and here I replaced the Q with J because that makes more sense in my opinion. You're welcome to bring it back to Q if you want, but Q makes no sense as heat, and J makes a little more sense as heat. Doesn't make much more sense, but at least it reminds you of getting joules when you're done. So if I need to know how much heat is needed or released when we're going from solid to liquid. You're putting heat in, and liquid to solid, you're taking heat out. How much heat is it? Well, it's 334 joules per gram. And when we do heat of vaporization, same thing. I have to give you this number, but you have to realize that vaporization is liquid to gas and gas to liquid. Now, thankfully, vaping is a thing now. Not thankfully, but because it's a thing now, is thankful for chemistry teachers all around the world who now can tell people, vaping is liquid to gas. And people's like, oh, yeah, I know that because of popular culture. This fusion being solid to liquid or liquid to solid is not something people are aware of. So to help you understand or remember that, I showed this video, which I guess I'll do right now against my better. So just hold on a second. If I were better prepared, this would happen already. DOT crown. There we go. And I guess that's the one I showed you. I like how I get that little circle there. Is it working? All right, it's coming. All right, so while that's coming, for some reason taking forever. All right, so what we're gonna do? We built up this whole scene with Aquaman and his wife and this guy, and what basically was the point is when we'll just jump here. All right, so he gets the triple point of gold by putting his WWE belt into the soup pot, and that would not really happen. But he gets solid, liquid, and gas all at once. And when he gets a nice liquid, he does this, right? And then we're not going to talk about this right now. But the end result, if we just jump to what happens, is it's fused to his head. It went from a liquid to a solid, and it fused to his head. So that's fusing, and because that's fusing, that hopefully liquid solid means fusing. So delta H fusion. All right. So moving on. So in the parts of the heating curve, 1, 3, and 5, 1, 3, and 5, where there's heating up a solid, heating up a liquid, or heating up a gas, you can use this equation that we've been using with specific heat because there's changing temperature. Temperature's changing here, it's changing here, and it's changing here. Here's the temperature. It's not changing in part 2 and part 4. Part 2 is the fusion, right? That's solid liquid or liquid solid. Because here's solid and here's, yeah. So let's make sure you know that. This is where solid exists. This is where liquid exists. And this is where gas exists. So solid to liquid or liquid to solid, that's fusion. And liquid to gas or gas to liquid, that's vaping. So that's heat of vaporization. All right. So when I ask you how much heat is absorbed when water boils at 100 degrees, this 100 degrees Celsius, even though it makes you think, hey, I need to use the specific heat equation, you don't. It's a red herring, and there's a red herring. It's just there to distract you. Water always boils at 100 degrees, but it doesn't change its temperature. So we're talking about this part here where water is boiling. So therefore, we need to use the heat of vaporization. There it is. We just multiply the mass to 8.75 times the heat of vaporization. So this number has to be given somewhere on your test. You have to go find it. And you multiply them, and you get that thing. All right. Whereas 1 mole of water from solid to liquid or 1 mole of water from liquid to gas, which uses more energy, you know that you're going to have to use your delta H fuse or your delta H vape. And your delta H fuse was, what was it? Since I got to give it to you, 334. Or did I give it to you? 334 or 2260. Okay, here we go. Hold on a second. So 334 or 2260 joules per gram. Joules per gram, right? Fusion has to do with solid to liquid, as we just saw from Game of Thrones, and liquid to gas, that is vaping. So liquid to gas is delta H vape. So the question is, if you have 1 mole, so the same amount, right? Water weighs 18 grams per mole. You get that from the periodic table. Hydrogen is 1, right? Hydrogen is 1. Oxygen is 16. There's 2 of those. So that's 2 plus 16 is 18. So 18 grams, if I'm going to use 18 grams of fusion or 18 grams of vaporization, the number for vaporization is going to be bigger because this is a bigger number. So converting 1 mole of liquid to gas requires more energy. All right. I already did that. Why don't I do it again? Anyway. Okay. So here is the reason sweat is supposed to work is because it's being evaporated off your body. That doesn't happen in North Carolina, but if you go someplace that's a little drier, you can get cold when you have water on your body, like in a pool, and you jump out of the pool. All the water evaporating cools you down like it's supposed to, or when you sweat, it cools you down like it's supposed to, because you're putting in that delta H vape. So here, if you had 500 grams of water leave your body because of sweating, that delta H vaporization is leaving your body. So it's taking that heat away from your body when you sweat. So 500 grams times 2260 joules per gram. That's how many joules you lose when you sweat. Okay. So you need to know when to use these things. And if you have a question here where there's a delta T, and you're talking about something that is dealing with just one substance. So here's ice, which is a solid. It's not changing its state, and it's heated from -40 to 0. That is going to use this equation because we have a delta T now. We have a 40-degree delta T. We have a specific heat for ice. If you look here, water as a solid is actually different than the liquid. It's 2.06 joules per gram degree Celsius. And then the mass is given right there is 250 grams. So we're going to use that equation to figure that out. So 250, hold on a second, 250 times 40 times 2.06. I think that's what this is. Yeah, is 20600. All right, so since there's a change in temperature, we're at that part of the graph where temperature is changing. Oops, hearing came a little early. All right, so we're talking about either the 1, 3, or 5, and in this case, it's the part 1. So that's why we use that one. This one where it's melting, so that's a change of state, we're going to use either fusion or vaporization. So we're going to need one of these things. And because it's melting, we're going to go with fusion. And the heat required for that would just be the 250 grams of ice times the delta H fusion, which is 334. So you need to know when to use these tools. And that's the point. And 250 times 334, I already actually had it, was 83500. There you go. Tools. Right. So you need to know when to use one of these. I will always give you specific heat chart like this. I will always give you these values, but you have to know when to use fusion, when to use vaporization. So in summation, you use the specific heat thing for these parts of the graph here because temperature changes. When temperature does not change, when you're melting or boiling something, you need to either use the melting one or the boiling one, the vape for boiling and the fusion for melting. All right. All right. And then I guess this has to do with, that's not as important, but this is important. We'll talk about AC and the thing, but I don't know when I really bring that up. Here's the point. When you put energy in, then it's endothermic. And when you take energy out, it's exothermic. So turning a solid to a liquid or a liquid to a gas, those are all endothermic as you're going up. Turning a gas to a liquid or a liquid to a solid, those are all exothermic because you got to take energy out. So increasing internal energy is endo, right? And going down would be exo. I think that's it. I don't think I need to wheel that. So those are those. We're going to discard all that. I hope that's helpful to you. And I finally did this thing so I can say that's done.